In this physics tutorial, you will learn 1. The meaning of dot, scalar, product, of two vectors, both geometrically and conceptually. 2. How to calculate the dot, scalar, product of two vectors. 2 methods. Point 3. Some applications of dot, scalar, product in physics. Introduction. In physics, there are many quantities that apparently are measured by multiplying the same vector quantities, and they seemingly are measured by the same unit, but which describe concepts that are totally unrelated. For example, work, W, is calculated by multiplying two vector quantities such as force, F, and displacement, or linear distance, delta x. However, there is another quantity known as moment of force, M, that is also calculated by multiplying force and the linear distance from the application point, the position in which the force acts, to the turning point. The equations for these two quantities are apparently the same. Since we have two different quantities obtained by multiplying the same vectors, force and linear distance, it is obvious that the two-vector multiplication procedures used to calculate the work and moment of force are different. This difference is outlined at the symbols used to express these multiplications. In the first case, the dot symbol is used to express the two vectors' multiplication operation, while in the second case, it is used with the cross symbol to represent the multiplication of the given vectors. This is not unintentional, rather, the two different symbols are used to demonstrate that here we are using two different techniques to find the product of two vectors. The first technique is known as the dot, scalar, product of two vectors, and the second one is known as cross, vector, product of two vectors. In this physics tutorial, we will deal only with dot, scalar, product of two vectors. The cross, vector, product will be discussed in the next tutorial. The meaning of dot, scalar, product of two vectors. Geometrically, the dot product of two vectors A and B, represents the numerical product of the magnitude of the vector A, and the projection of the vector B in the direction of A. Look at the figure on screen. How to calculate the dot product of two vectors. If we appoint a basic direction, for example O, x, to the first vector A, we write as b, x, instead of b, a, the component of the vector b in the direction of A. It is obvious the component of vector b, perpendicular to A, is denoted as b, y, instead of b, a. Also, we can appoint a letter, for example theta, to the acute angle formed by the vector A, or its extension, and the vector B. Therefore, the figure is written as shown on screen. The component, B, y, is equal in length to the opposite side to the angle, theta, for the triangle shown in the figure. Therefore, we can close this triangle to form a right triangle as shown on screen. From trigonometry, it is known that in a right triangle, we get the equation as shown on screen. Therefore, for the dot product of the vectors, A and B, we can write. It is obvious the previous mentioned product represents a scalar, C, not a vector, because we found it by multiplying two vector magnitudes, which are simply numbers, and the cosine of an angle. Hence, if we denote by C, the dot product of two vectors, A and B, we obtain the equation shown on screen. Example 1. Mechanical power, P, in physics is alternatively defined as the dot product of force, F, exerted on an object and the velocity, v, gained by the object due to the action of this force. A 120 n force acts at an object at 200 to the horizontal direction as shown in the figure. As a result, the object moves at constant velocity by a magnitude of 0.4 meters per second. Calculate the useful power delivered by the source in watts. 1 watt equals 1 joule per second. Take, cos 200 equals 0.94, sin 200 equals 0.34. Solution 1. As stated above, by definition, power is the scalar product of force and velocity. From the mathematical definition of the scalar product of two vectors, we know that to find the dot product of two vectors, we must multiply one vector with the component of the other vector in the direction of the first one. In this specific case, the movement occurs in the direction of the velocity vector. Therefore, we take the velocity vector as the first one and express the direction of force vector in terms of it. Thus, we must multiply in scalar mode the velocity vector, v, and the component of force, F, according to the direction of v. This means we have to calculate the following. After substituting the values, we obtain the following. Another method for calculating the dot product of two vectors. Calculating the dot product using coordinates. If the coordinates of the two vectors are known, it is much easier to calculate their dot product. We don't need to know the angle in between or the magnitudes of the vectors. We can use the formula as shown on screen. The previous formula is particularly useful when none of the vectors lies according to a main direction, axis. Thus, instead of trying to calculate the angle in between by finding the difference of two angles, the angle formed by the vector, u, to the horizontal axis minus the angle formed by the vector, v, to the horizontal axis, look at the figure on screen, and then expressing the direction of the second vector in terms of the first one. It is much easier multiplying only the coordinates as no angle is needed here. For simplicity, both vectors are taken with their origin, dale, at 0, 0. The procedure to calculate the angle between the two vectors is quite long. First, we need to find the angles formed by each vector to the horizontal direction by considering the tangents, y-coordinate x-coordinate. After finding each tangent, we find the respective angles using a scientific calculator. Afterwards, we subtract the angles to find the angle between the two vectors. Finally, we can use the dot product formula to find the result. As you see, it is not worth trying it. By using the new formula of dot product, we find the result in a much easier way. Thus, from the figure you can find all coordinates you need. There are x, u, equals 7 units, x, v, equals 13 units, y, u, equals 10 units and y, v, equals 4 units. Substituting the above values, we obtain the equation shown on screen. Dot product applications in physics. There are many applications of dot product of two vectors in physics. We will mention only a few of them. 1. Work as a dot product of force and displacement. We have discussed earlier, in introduction, this point. If you multiply in scalar mode the force exerted by an object and the displacement of the object due to the action of this force, the result will be a scalar quantity known as work and measured in joules. It is meaningless to say the work done by the force, F, is 300 J, due east, for example. We simply say the work done by the force, F, is 300 J. As work is a quantity related to the change in energy of a system, it does not involve any direction. 2. Power as a dot product of force and velocity. We discussed this point earlier in the solved example. If we multiply in scalar mode the two vector quantities, force and displacement, we obtain a scalar result that is power. It does not involve any direction as well. 3. The angle between two forces acting on the same object. Let's consider again the solved example in the previous section. Let's take the previously mentioned vectors as force vectors and the units as newtons. We found the dot product of vectors, u, and v, and it was 131 units. Now, let's calculate the magnitudes of each vector. From the tutorial Vectors and Scalars in Physics we know that therefore, we obtained for the angle between u and v. Therefore, the angle between the two vectors, u and v, is cos -1, 0.789, equals 37.890. This result was obtained much easier than if we used the long method described in the previous section. 4. Kinetic energy as a dot product of linear momentum and velocity. Kinetic energy of a moving object, a scalar quantity measured in joules-like work, is calculated through the equation shown on screen. M is the mass of the object and v is its velocity. However, since the linear momentum of a moving object is p equals m times by v, we obtain for the kinetic energy, K, E, the following equation. Therefore, kinetic energy can be expressed as the dot product of two vectors, p and v, multiplied by a constant 1 divided by 2, which only changes the result, it does not breaks the above-mentioned rule. These were some examples showing the most important applications of dot product in physics. We hope you found this tutorial useful. If you did, please take the time to rate this tutorial, or share on your favorite social network. In our next tutorial, we explore cross-vector product of two vectors.